So the balanced reaction equation starts with propane mixed with oxygen and nitrogen. The ratio between oxygen and nitrogen in air is 1 to 3.76 by mole. And it is a complete combustion. Therefore, carbon becomes carbon dioxide. Hydrogen becomes water. So we have carbon dioxide, water, and let's see, how many carbon dioxide and water we can create. So we have 3 carbon atoms in here, so that means we can create 3 molecules of carbon dioxide, 8 hydrogen atoms here. That means we can create 4 water molecules per molecule of propane. So then how many oxygens do we need? So we need 6 oxygens here for the carbon dioxide and 4 oxygens here for the water. So total we need 10 oxygens. And since 1 molecule of oxygen has 2 oxygen atoms, that means we need 5 moles of oxygen. However, as you can see, we are going to burn this propane with 200%, not 100%. So we are going to provide 2 times of this 5 moles of oxygen. So it becomes 10. And since we are providing 200%, so we have oxygen left over in the product because we are providing more oxygens than we require. And of course, nitrogen is not going to react. So there's a nitrogen at the end. So we just need to determine how many moles of oxygen and nitrogen are needed for this reaction. So we have 10 moles of oxygen. So that means 10 times 2. So we have 20 oxygens. And for this carbon dioxide, 3 times 2, we have 6 oxygens. 4 times 1, 4 oxygens, together 10. So out of 20, we only used 10. So 10 oxygen atoms are left over. Since 1 molecule of oxygen has 2 oxygen atoms, 10 oxygen atoms can create 5 molecules of oxygen. What about nitrogen? 10 times 3.76. 10 times 3.76, that is 37.6. That's how we determine the balanced reaction equation. In your first exam, for any combustion process, you need to be able to determine this balanced reaction equation. That's the first thing you need to do. And once you have this balanced reaction equation, then you can, you can solve energy balance equation. Okay, so this is the first step. Then let's write the balanced reaction equation. Energy balance equation. So the energy balance equation is simple. We have a combustion chamber. We have an inlet, and this is combustion chamber. We have an exit. At the inlet, we have propane and oxygen and nitrogen. At the exit, we have carbon dioxide, water, oxygen, and nitrogen. And this process, this combustion process, is going to create heat. So there's a heat transfer from this conversion chamber to the outside. So there is Q out. If we use rate form, since it is an open system, we can use Q dot. Then what is the energy balance equation? The energy transfer in per unit time is the same as energy transfer out per unit time. So E dot entering the chamber is the same as E dot leaving the chamber. So how many E dot? By the way, we are neglecting any kinetic energy change or potential energy change. Then how many energy transfer rate do we have that go into this conversion chamber? We have propane, oxygen, and nitrogen. Then how do you determine the energy of propane, oxygen, and nitrogen? Since they are entering the chamber, we can use enthalpy. So H, so this the rate of energy transfer in first. The rate of enthalpy, H dot of propane, C3H8, plus the rate of enthalpy by oxygen, H dot of oxygen, plus the rate of enthalpy, H dot of nitrogen, is the same as the rate of energy leaving this conversion chamber. First, we can think about the rate of heat transfer, Q dot out, plus how many components at the exit? We have a carbon dioxide, water, oxygen, nitrogen. Carbon dioxide, H dot of carbon dioxide plus H dot of water plus H dot of oxygen plus H dot of nitrogen. So that is the energy balance equation, assuming that there is no kinetic energy change or potential energy change. Then how can we determine H dot? Oh, it's right here, this one. H dot can be determined by, so H can be determined by mass times H bar, which can be determined by mass times the enthalpy of formation plus delta H. If it is H dot, it's going to be M dot times, this is N. N dot times enthalpy of formation plus delta H bar. So we are going to write we are going to replace each H dot with N dot times the enthalpy of formation plus delta H bar. You will do exactly the same in your first exam. Okay? You determine the balanced reaction equation. You write the energy balance equation based on the balanced reaction equation. Determine each term by this form, and that's all. There are only 3 problems. If you miss one, it's going to be big trouble. Okay? So if you don't know how to solve this one, then it's going to be a problem because there are only 3 problems in the first exam. Okay, so yes. The day for the exam depends on how we progress today. So if we finish everything today, it's going to be a week from today. So yeah, that can be your plan. What? Oh, you want to have a review? Then we can do a review next Thursday, and then we can have an exam the following Tuesday. That works better, right? So you can have a nice full break, right? That's also what I want to do. I also extended, the other class homework due date to, yeah. Oh, for this one, the second one, a week from we finish this chapter. So that's going to be Thursday. But if you want that due to be on the same day of your first exam, I can do that if everyone like that. Huh? Okay. So again, this thermodynamics, again, I'm telling you, this thermodynamics, there is no surprise. Everything is what we have done in the classroom. You will do the same with the different numbers, with the different, the geometry in the exam, okay? So what we did in the first part of this thermodynamics 2, we studied a dehumidifier. And you remember how to, write the energy balance equation and mass balance equation, one for dry air, the other one for water vapor. You will see a problem like that. And the other, the problem, another problem you will see in the first exam, you will determine the balanced reaction equation. You will write the energy balance equation based on the balanced reaction equation and solve for an unknown. And then what will be the last problem? What is the, the governing equation that we haven't brought in here? Entropy balance equation. So those are the three problems. I'm disclosing everything, okay? So technically, if you just follow, what I ask you to do, do the problems in the PowerPoint, do the homework assignments, you know everything. The first one is the energy balance equation for dry air and water vapor mixture, and we solve those problems together in the classroom. This is the second problem. You will write the balanced reaction equation and energy balance equation to determine any unknown. The last one is going to be entropy balanced equation that we will do today. So today's lecture contains two problems, 66% of the first exam. That important. So today is that important. Okay, so this H dot can be written by N dot enthalpy of formation and delta H bar. So I'm going to replace each one with that. So starting with this propane, this one is going to be N dot times enthalpy of formation plus delta H bar. This is for propane. And we have the rate of enthalpy for oxygen. N dot times the same form. The enthalpy of formation plus delta H bar. This one is for oxygen. And we know what comes next for nitrogen. N dot, the enthalpy of formation plus delta H bar. This is for nitrogen. And this red one, the rate of heat transfer. I'm going to use this red. Q dot out, this is what we want to determine. And we have H dot for carbon dioxide. So it's going to be N dot the enthalpy of formation plus delta H bar. This is for carbon dioxide. We have 3 more to go. I like thermodynamics, except that this energy balance equation is just too long. And my right hand hurts. Plus, now this time water, and that the enthalpy of formation plus delta H bar. This is for water, but if we just keep repeating the same form, too boring, right? So there's something fun happens here. Now we have a water. Whenever we have water, there's a problem, right? What problem is that? There are 2 different waters that we remember. If you remember the property table, which is table A25 that we are going to use. Where is the water? Right here. Oh, there are 2 waters, right? One is water vapor. The other one is liquid water. So whenever you have water in a combustion process, you need to determine the phase of this water. So how are we going to do that? You need to see the temperature and pressure of this water. So this water is at the exit. So what is the exit condition? 1 atmospheric pressure, 560 Kelvin. So when you have this temperature and pressure, can you determine the phase change process of this water? Yes, you can. We can make property diagram, PV or TV, and then find our the system on the diagram. But this time we don't have to do that, because what is the pressure? 1 atmospheric pressure. What is the saturation temperature of water at 1 atmospheric pressure? Yeah. So what is the temperature? Greater than 373. So what is the phase of this water? Yeah, gas. So this water is gas. So we don't have to worry about that. Plus, then if you read this problem statement until the end, you may see what is the exit temperature. 298 for the second part. So in that case, we may have liquid, vapor together. Whenever in thermodynamics, liquid, vapor together, what happens? Things are complicated, right? So the second part is going to be complicated, but first part is not, because it's just pure gas. Okay. Then what comes next? We did water, and now we have oxygen. Plus, and that times the enthalpy of formation plus delta H bar. This is for oxygen. Plus, we have nitrogen. And that the enthalpy of formation plus delta H bar. This is for nitrogen. So this is the energy balance equation. Energy balance equation. So what we are going to do? Now we know what we are going to do. We are going to evaluate each property one by one. So how many? 1, 2, 3, 4, 5, 6. By the way, this delta has 2 properties, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Just many, right? So we are going to evaluate these many properties. Then you will be able to determine this Q dot. The good thing about thermodynamics is it's not that difficult, but it's just taking so much time, right? So that's the problem. So now you can see how you're going to prepare the first exam. Why there are only 3 problems? Because it's going to take a lot of time. So how can you finish everything on time? You need to practice as many times as you can on all the problems that we did in the classroom. And homework assignments. The same as Thermodynamics 1. Just keep practicing, you will get 100 out of 100, right? So, but this is not that bad because now it's a fun time. Whenever you write a long energy balance equation, the good thing is, do you remember how to determine the simple version of energy balance equation for open system? You cancel, cross them out, right? A lot. That's what we are going to do. So first, the enthalpy of the n dot first. What is n dot? The molar flow rate of each component. Then, to solve this one, we need to make an assumption. The assumption is going to be the molar flow rate of the main component, propane. I'm going to say n dot of propane is going to be 1 kilomole per second. So that is our assumption. So that's my assumption. Then what is n dot for propane? That's 1. What is n dot for oxygen? If the n dot, the molar flow rate of propane is 1, what is the molar flow rate of oxygen? What is the ratio between propane and oxygen by mole? This is 1, 10. So if the molar flow rate of propane is 1, molar flow rate of oxygen is going to be 10. The molar flow rate of nitrogen is going to be 10 times 3.76. The molar flow rate of carbon dioxide is going to be 3. The molar flow rate of water is 4, 5, 3.7, 37.6. So we know n dot for every component. They are from the balanced reaction equation. So if we assume that this is assumption, 1 kilomole per second, then this is going to be 10. This is going to be 37.6. This is going to be 3. This is going to be 4. This is going to be 5. This is 37.6. Okay. That wasn't bad. Yes. Yeah. Then everything is based on this assumption. So if the flow rate of the propane is different, then you just need to multiply by that number to determine Q dot. So this Q dot is going to be per kilomole per second of propane. Then if you want to determine another value, maybe this, the Q dot for this much propane, you just need to multiply by the amount of propane. Then you get Q dot. Any question up to here? So the first thing is that determining all the, the molar flow rates, n dot. Once you determine n dot, now it's the time for enthalpy of formation. It's going to be your grass is dying. Huh? They already, did something this morning on my yard, and they're calling again for the next one. I need to open up, the True Green office somewhere in Mount Pleasant. Okay, so the first four components, carbon, hydrogen, nitrogen, oxygen, the enthalpy of formation values are 0. So you got True Green too? So in this case, we have an oxygen, nitrogen, oxygen, nitrogen. What are the enthalpy of formations for oxygen and nitrogen? 0. So where is the enthalpy of formation for oxygen? This one. This one is 0. Nitrogen. This one is 0. Oxygen. This one is 0. Nitrogen. This one is 0. Then what do we have? The enthalpy of formation of propane, carbon dioxide, water. So let's find those threes. from the energy balance, the table, from the table. Where is the table? Where is the table? Oh, right here. To determine the enthalpy of formation, you go to table A25. A25 for the enthalpy of formation. Okay? So let's go to table A25. Here is table A25. What do we have? Carbon dioxide, water, propane. So there's a propane, water, and that is a water vapor. Carbon dioxide. So the enthalpy of formation values are available here. So this is propane. The enthalpy of formation is this number. There's a water vapor, this number. There's a carbon dioxide, this number. So let me write these three values on this energy balance equation. Propane first. The enthalpy of formation is minus 103,850. What is the unit? Kilojoule per kilomole. Kilojoule per kilomole. What about carbon dioxide? This one, minus 393,521, kilojoule per kilomole. And water vapor, this one, minus 241,820 kilojoule per kilomole. Okay, any question up to here? Yes. Okay, so if you come back to this slide, table A25, the enthalpy of formation of carbon, hydrogen, nitrogen, oxygen. There is no enthalpy of formation. Okay. The more nitrogen, more oxygen you have in the balanced reaction equation, you must be pretty happy because you can cross them out. Then the next one, delta H. What is delta H? Delta H bar is the enthalpy of formation is only valid at the standard state, which is, so this enthalpy of formation is only valid when the temperature is 298 Kelvin, 25 degrees Celsius, 1 atm. What about if the temperature of our system is different from this temperature? Then that's when we use delta H bar. So this delta H bar is H bar at the given temperature minus H bar at the standard state, 298 Kelvin. So if the temperature is different from this one, then we use this one to correct the enthalpy of formation. Then what is the temperature of the reactant? The temperature of the reactant is 298, 1 atmospheric pressure. So that is exactly the same as the standard state. So what is delta H? 0. So this is the standard state, standard state, standard state. What about at the exit? Exit is at 560. So that is different from this number. So we need to determine delta H bar of the carbon dioxide because the temperature is higher than the standard temperature, and also water, oxygen, and nitrogen. So starting with carbon dioxide first. So this one can be determined by H bar at the given temperature. I'm going to answer this. Hello?
Quarterly test of the central alert system. This is only a test.
Okay. Let's go to the test, right? We have a test coming. All right, so H bar at 560 Kelvin minus H bar at 298 Kelvin. So that's how we determine delta H. This is for carbon dioxide. Then how do we determine this delta H bar? From another table, this time table A23. Table A23. So let's go find table A23. And what is our material? We have a carbon dioxide, 560 and 298. Where is carbon dioxide? These three properties are for carbon dioxide. And what are the temperatures? 560 and 298. So there is a 298 here. What is H bar? This number, and so 9,364. 9,364 kilojoule per kilomole. What about at 560? Okay, 560 right here. 560. H bar is going to be 20,407. 20,407. 20,407. That is H bar at 560. So that's how we determine delta H bar for carbon dioxide. Now we need to do 3 more times. Water vapor. We go to the same table, A23. Now this time, where is water? Water vapor, this one here. So at 298 and 560, at 298, H bar for water is this value. At 560, H bar of water is going to be 18,959. Oh, where is it? Not yet. I need more space. Okay, this one. This can be determined by H bar at 560 minus H bar at 298. And 560. This one, 18,959. 18,959. What about 298? 9,904. 9,904. So that's how you determine delta H bar for water vapor. We do the same for oxygen this time. So this one, oxygen. I don't like this problem. So H bar at 560 minus H bar at 298. So where is oxygen? Here. So let's find H bar at 298. This number. H bar at 560, this number. So you see these two. This one is H bar at 560, H bar at 298. So this one is 16,654. H bar at 298, 8,682. then finally, nitrogen. Where is nitrogen? The last three columns. So H bar at 298, this number. H bar at 560, this number. So 60. Write it here. H bar at 560 minus H bar at 298. So this one is 16,363, 8,669. That's how you find all the values in this energy balance equation. Any question? This one completely blocked my screen. Test. Then we have everything but Q dot out, right? So can you determine Q dot out? Now, yes, we can. Q dot out is, where's my solution? One million, 1,645,299 kilowatt. This is for 1 kilomole per second of C3H8, right? That was our assumption, right? Now, what is the flow rate of propane? 0.7. So we just need to multiply by 0.7. Then what is Q dot out? 1,152 times 10 to 6 kilowatt. So you solve this energy balance equation for 1 kilomole per second of propane. And once you solve this energy balance equation to determine whatever you're looking for, then you need to multiply by the flow rate of your system. That will give you the right heat transfer rate. Any question? Was it difficult? I know it takes a lot of time, but was it difficult? So three steps. Write the energy balance equation. So write the balance direction equation and write the energy balance equation and convert into the final form and find each property from a property table. So if I give you this problem in your first exam, can you solve it? It takes time. So what do you think I'm going to do? I will simplify this process. Maybe I can give you, the balance direction equation. Then you can just start from here. Maybe I can, I can tell this is not air. This is just oxygen. Then we can remove nitrogen. Or I can just say, instead of propane, maybe just carbon, which will be much easier because there will be no water. So there are many ways I can simplify this, problem. So when you are in the exam, you need to catch, the how to, write the energy balance equation and find their properties. Yeah. Okay. H bar degree F, this is enthalpy of formation, right? And the enthalpy of formation of 4 components carbon, hydrogen, nitrogen, oxygen, there's no enthalpy of formation. So you can cross them out. That's how we crossed out the enthalpy of formation. Then how did we remove this delta H bar? This delta H bar is given to correct the enthalpy of formation if the temperature of the product is a different temperature than this one. Because the enthalpy of formation that we got from the table is only at this temperature. What about the temperature of your oxygen is different from 298? Then we need to correct that, the difference, right? Delta H bar is the difference. So if the temperature of your system is at 298, do we need to write this in? Do we need to use this difference? No. Then you can cross them out. Make sense? Because the given temperature is 298 minus 298, 0. But this is not the worst. Now the problem is going to be repeat for an exit temperature of 298. So we need to repeat the same thing at 298. Maybe one can say, oh, it's not 560 anymore. It's only 298. So we don't need to worry about delta H bar. You're right. But there's another problem comes, which is when we write this balanced reaction equation, our assumption is this water is gas. This water is gas because the temperature is just too high, right? It's 1 atmospheric pressure. What is the boiling temperature? Oh, we cannot say boiling temperature. We studied thermodynamics. What is the saturation temperature? 100 degrees Celsius. This one is greater than 100 degrees Celsius. So we know it's a superheat vapor, completely gas. But at 298, what is the phase change process? You may have liquid, you may have vapor. So we need to determine the ratio between liquid and vapor when we are not sure the phase change process of this water. Okay? So that's what we are going to do. So that one was not the final boss. This one is 298. So you must be very excited to challenge this second problem, okay? So I'm going to write the energy balance equation one more time. So the energy, balanced reaction equation, C3H8 is going to react with 10 oxygen, 3.76 nitrogen plus 3 carbon dioxide plus 4 water vapor. Not anymore, because the temperature is 298. Really? Before we just assume that, oh, there should be liquid and vapor. Let's verify whether it is liquid or vapor altogether. How can you verify that? You studied it. How can you check there is liquid and vapor together? When this vapor becomes liquid, from the previous chapter, when vapor becomes liquid, when you have foggy windshield, dew point temperature. Dew point temperature. Do you remember that? Dew point temperature. When dew point temperature is, when the temperature is less than the dew point temperature, then you can say there is a liquid water. When the temperature is greater than dew point temperature, then you don't have to worry about that. So let's see. Let's determine the dew point temperature. How can you determine dew point temperature? What is dew point temperature? Dew point temperature is the saturation temperature of the partial pressure of water vapor. So now you know you can see what if I give you remember that last week I told you that what about if I give you a sub problem to the first part of this thermodynamics 1, thermodynamics 2, what is the dew point temperature in this condition? So this is a good time to review how to determine dew point temperature. So dew point temperature means T dew is the saturation temperature at the given pressure. But what kind of pressure? Any pressure? 1 atm? No. We are talking about what? Are we talking about air? Dew point temperature of air? No. Dew point temperature of water. So what is the pressure? Pressure of air? No. Pressure of water. Then what is pressure of water? 1 atm? No. This 1 atm, which is the pressure of the mixture, is T of air plus P of water vapor. Then what is the pressure that we are going to use to determine the saturation temperature? Air never goes to saturation. It's going to be a vapor. So this pressure is going to be a vapor pressure. That means we need to determine the vapor pressure, the partial pressure of water vapor. How do you determine the partial pressure of water vapor? We studied it on day 1 when we started thermodynamics 2. The partial pressure of water vapor can be determined by the mole fraction of water vapor times the mixture pressure. And here the mixture pressure is what? 1 atm. So this one is 1 atm. Then to determine this partial pressure, once you determine partial pressure, now it's simple to determine saturation pressure. We just need to go to saturation table for pressure. And the question is, how do we determine this mole fraction of water vapor? Then how can we determine the mole fraction of water vapor? Do you know how to determine the mole fraction? Yes, the mole or the number of moles of water vapor over the total number of moles. Then how many moles of water vapor do we have? We're talking about the product. How many moles? 3? 37.6? 5? 4? Yes, 4 is the number of moles of what? Water vapor. 4. What about the total number of moles? How do we determine the total number of moles? 3 plus 4 plus 5 plus 37.6. That is 49.6. You're not very interested in this dew point temperature. So there will be one problem in the first exam to determine dew point temperature. Now we are excited, right? So again, if you want to determine dew point temperature, let me repeat that again, just for your review. To determine dew point temperature, please focus on here because it's interesting. Not interesting? You're majoring this one, so it's supposed to be interesting, right? So T set at the partial pressure of water vapor. So I'm going to say just vapor pressure. So the vapor pressure, the saturation temperature at the vapor pressure is the dew point temperature. Then we need to determine the vapor pressure. How do we determine the vapor pressure? The mole fraction of vapor times the pressure. Pressure is 1 atm. Then how do you determine the mole fraction? N of water over N of everything. Our assumption is everything is vapor. Let's determine dew point temperature. Is it greater than this one or less than this one? That's how we determine condensation. So our assumption is that everything is vapor. That's our assumption. Because we need to check whether it is completely vapor or not. So from here, you can determine the mole fraction. We know the partial pressure of water vapor, that is 1 atm. By the way, we are going to use bar, that is going to be 1.01325 bar. Then we have everything. Can you determine the partial pressure of water vapor? Yes, it is 0.08172 bar. Okay, now we have the vapor pressure. Let's determine the saturation pressure. How do you determine the saturation pressure when you have vapor pressure? Do you remember how to determine saturation pressure? That's what we did long time ago when we studied Thermodynamics 1. You go to saturation table for water, pressure table, table A3. So there is a table A3. Oops, stop. So this is the pressure, right? 0.08 something. Let's find that pressure. 0.08 something. So you need to do linear interpolation between these two numbers to determine T set. T set is going to be 0.08172 is going to be slightly greater than 41.5. If you do the calculation, the dew point temperature is 42. So from this, T set is going to be 42 degrees Celsius. That is dew point temperature, 42 degrees Celsius. Okay, now we determined the dew point temperature. What is the temperature at the exit? 25 degrees Celsius. So compared to this 42, 25 degrees Celsius is less than this one. So is there condensation? Yes, there is. So now we need to determine one more thing. We need to determine, okay, so there's a condensation, but how much condensation? Out of 4. So this is a little tricky part. So to determine the amount of condensation, we need to write down the balanced reaction equation. So according to this one, yes, there is a condensation. So not just water vapor. Now we have water vapor and water liquid plus oxygen 5 plus nitrogen 37.2 6 nitrogen. Now, the problem is going to be, okay, we know there's a condensation, so we should have water vapor, we should have liquid water, but how much water vapor, how much liquid water? I'm going to say the number of moles of water vapor, that's what we want to determine. I'm going to say this is, let's say, X. Then what is this one? Y? No, what is this one? If this is X, what is this one? What is the total amount of water? Out of 4, if this water vapor is X, what is the amount of liquid? 4 minus X. Now, we are going to recalculate vapor pressure. So previously, when we assumed every water is in the vapor phase, this is very important. We assume that every water in the product is in the vapor phase. That assumption, with that assumption, we calculated dew point temperature. But this dew point temperature, 42 degrees Celsius, is only when we have 100% vapor. Now we have some liquid, some vapor, right? So what is the dew point temperature? Still 42? Not anymore. What is the dew point temperature? Up there, 298. That's the dew point temperature. So this time I'm going to say the dew point temperature is T dew is 298. That is 25 degrees Celsius. If you know the dew point temperature, can you determine the partial pressure? Yes. By how? Pressure when saturation pressure at 25 degrees Celsius is the partial pressure of water vapor when the dew point temperature is 25 degrees Celsius. And how can you determine P set at 25? Now, temperature table. Now I need to think about, the adding this dew point temperature in the first exam or not. So at 25 degrees Celsius, what is the vapor pressure? 0.03169. 0.03169 bar. If you're not that interested here, then maybe I can remove the entropy balance equation and put several dew point temperature calculation in the first exam. Yes. So we got this dew point temperature, assuming that every water is in the vapor phase, and the temperature is less than that. So we show that there is a condensation. Now, assuming there is a condensation, the amount of water vapor is not as much as this dew point temperature. So we need to recalculate dew point temperature. That temperature is the exit temperature. Right. So we are going backward this time to determine the mole fraction of water vapor. Now, assuming the dew point temperature is the same as the exit temperature. I definitely need to put this one on the exam one. So now this is the partial pressure of water vapor, that is 0.03169 bar. And how do you determine this partial pressure of water vapor? By the mole fraction of water vapor times the pressure of the system. And what is the pressure of the system? 1 atm. 1.325 bar. From here, you can determine the mole fraction. The mole fraction from here. So what is the mole fraction? 0.03128. Then how do you determine this mole fraction? Number of vapor, water vapor, divided by the total number of moles. Then going back to this balanced reaction equation. What is the number of moles of water vapor? 3, 5, 37.6, 4 minus X, or X? X. We're talking about vapor. So number of moles is going to be X. How do you determine the total number of moles? 3 plus X plus 5 plus 37.6 plus 4 minus X? Not anymore, because 4 minus X is the number of moles of liquid. That's not a part of the gas. So this time the number of moles can be determined by 3 plus X. Oh, that is not vapor anymore. Go away. It doesn't affect the pressure. Plus 5 plus 37.6. If you solve it, you get X. If you solve it, you get X. X is, where are you? 1.4724. 1.4724. Then coming back to this balanced reaction equation. This one is 1.4724. This one is 4 minus 1.4724. So what is the balanced reaction equation? C3H8 plus 10 oxygen plus 3.76 nitrogen plus is going to be 3 times carbon dioxide plus this one. Let me use this red. 1.4724 water vapor plus liquid water. 4 minus this number. 2.5276 water, but this one is liquid, plus 5 oxygen plus 37.6 nitrogen. So that is the balanced reaction equation. Then we write the energy balance equation. H dot for propane plus H dot for oxygen plus H dot for nitrogen is going to be Q dot out plus H dot for carbon dioxide, H dot for water vapor plus H dot for water liquid plus H dot for oxygen plus H dot for nitrogen. I told you that this is the final boss problem, right? But further, when you play Super Mario, Super Mario not that fun anymore. GTA, I haven't played it. That's something like, you know, that you steal a bike and ride. I remember that playing that one. It was fun. Okay, but what was the final boss in the game? There was no final boss, right? It was like, you know, the keep going, right? Never end. Okay. So let's solve this one. N dot times the enthalpy of formation plus delta H bar. This one is for propane. Now you know how to write this energy balance equation because this is not the first time, right? Delta H bar, this is for oxygen, and that the enthalpy of formation plus delta H bar, this is for nitrogen, is Q dot out plus N dot, this one is for what? Carbon dioxide. H bar degree F plus delta H bar, this one is carbon dioxide, N dot, the enthalpy of formation, delta H bar, this one is water gas. Down here. Plus N dot, the enthalpy of formation plus delta H bar, water liquid. I need a propane or something. Then oxygen and nitrogen. And that, and the enthalpy of formation plus delta H bar. This one is for oxygen plus N dot, the enthalpy of formation plus delta H bar. This one is for nitrogen. Okay, N dot first. Now you know how to do that. N dot first. We assume that this one is 1 kilomole per second. What is this one? 10. What is this one? 37.6. What is this one? 3. This one. 1.4724. This one. 2.276. And this one. 5. 37.6. Now, the enthalpy of formation of nitrogen and oxygen. What is it? The enthalpy of formation of oxygen and nitrogen. 0. Go away, go away. This one, this one. What is the temperature at the inlet? 298. What is the temperature at the exit? 298. Do we need to determine delta H? No. So you can cross this one out. This one, this one, this one, this one, this one, this one, this one. So we have the enthalpy of formation of propane, carbon dioxide, water, and that's all. So now let's find them. This one first. Let's go to table A25. Propane first. Where is propane? Minus 103,850. Minus 103,850. Water vapor minus 241,820. Water liquid minus 285,830. Minus 285,830. So we have everything. Can you determine Q dot out? Yes, we can. From this equation, Q dot out is going to be minus 2.155 times 10 to 6 kilowatt. But this one is for 1 kilomole per second. So we need to multiply, and we need to determine this one by 0.7 kilomole per second. So Q dot out is going to be this one multiplied by 0.7, 1.5085 times 10 to 6 kilowatt. So if you are able to solve this problem, you know how to determine the balanced reaction equation, you know how to determine the energy balance equation, you know how to determine the dew point temperature. Any question? Since we are running out of time, we cannot finish this chapter today. So next Thursday, we are going to study the last part, entropy balance. So the exam is going to be the following Thursday. Thursday, because there's no Tuesday class next week, have a happy fall break. Okay.